Right, now we are starting section 3.2 in this video. In the previous video, in the section 3.1, I introduced you systems of linear systems of differential equations. Now in this section, I'm gonna just review what are the linear systems and how can I represent these linear systems using matrices. If you have taken linear algebra before, then you should be already familiar with all these concepts. But if you have not taken linear algebra before, then you need to remember, you need to know all these important facts, okay? So in this video and in this section, we are gonna cover these concepts quickly, not into much detail. So what I suggest you, if you don't understand it, you can just go back and look at some linear algebra notes, your linear algebra notes, or if you haven't taken linear algebra, try to find a way to learn, okay? All right, so let's get started. So first of all, what's a matrix? An n by n matrix, we show matrices by two numbers, okay, like 3 by 2. An n by n matrix has, matrix A has m rows and n columns, okay? For example, I can write A as 1, 7, 25, 2, 3, 4, okay? So A is an 2 by 3 matrix because there are 2 rows and 3 columns. And of course, these entries can be any numbers. It doesn't have to be an integer. It can be a real number. It can be a complex number, any numbers. All right. So this is the definition of a matrix. What's the vector? A vector with R entries is then denoted by, we are just taking one column of a matrix. If you just take one column of a matrix, then it's called a vector, okay? A scalar, when I say scalar, just a number, but you can think that number as a one by one matrix as well, right? Maybe I can give an example to by the way a vector. For example, let's look at this vector. Let's just take the first column of the A matrix, okay? This is a vector. And its scale is just a number. And whenever we have matrices, we can have addition, subtraction, multiplication, and scalar multiplication either. So first of all, what is the scalar multiplication? For example, if you have a matrix, 1, 2, 3, 4, 5, 6, this is a matrix, right? And if you multiply a matrix with a scalar, you just multiply each number in the matrix with that scalar, okay? So 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and so on and so forth, okay? And what about addition? Can we add matrices? The answer is yes, but it depends. We can add the matrices only if they have the same dimension, okay? If they have the same number of rows and columns. And addition is just component-wise, okay? For example, this is A, this is a 2 by 2 matrix, this is B, this is a 2 by 2 matrix. So A plus B will be just 1 plus 5. So 1 plus 5, this is the first entry. 2 plus 6, second entry. 3 plus 7 is the next entry. 4 plus 8 is the last entry. So A plus B is actually equal to 6. 2 plus 6 is 8, 10, 12, okay? So just add component-wise. So 1 plus 5, 2 plus 6, all right? Can we multiply matrices? Again, the answer depends, yes, but it depends. And to be able to multiply matrices, what is the condition? Number of columns of the first matrix should be equal to number of rows of the second matrix, okay? So if you are, for example, multiplying an n by r matrix times r by n matrix, I can apply this multiplication because these are the same numbers, right? Remember, second number in a matrix representation shows the number of columns. So number of columns is r here, number of rows is r here. So they are same, so I can multiply them, okay? And the answer would be n n by n matrix, okay? You just cross out these r's and you're just taking m and n, all right? And by the way, if you can multiply a and b, in most of the cases you cannot multiply b and a. And I have examples for multiplication in the next slide, in the next page. Let me continue. Another important concept of matrices is actually the identity matrix. The identity matrix is square matrix, which means square matrix means number of rows equal to number of columns. So it's the square matrix. It's zero elsewhere, but only non-zero entries are on the main diagonal, and they're all one. Okay. For example, this is a 3 by 3 identity matrix. And what are some nice properties about matrices, matrix operations? So you can, as you see here, you can group them together in the multiplication. You can distribute matrices from right or left. You can distribute this scalar elsewhere. And also identity matrix times a matrix is equal to itself from both directions, all right? Okay. So I didn't want to do that. All right, let's go to the next page. I think I can do that in only one video. Oh, okay. Come on. All right. Okay. A few warnings. In general, A times B is not equal to B times A. Yes, this is what different in matrices from numbers. Okay. And if A times B is equal to A times C, you cannot just simplify A's and say B is equal to C. And it's only true if A is not, even actually it is not true. You cannot simplify A and just say B and B is equal to C. And it's also interesting that if A times B is equal to 0, it doesn't necessarily mean that A is equal to 0 or B is equal to 0. They can be both non-zero matrices, but the multiplication can be 0. Okay, these are a few warnings. What about inverse of a matrix? Actually, we talk about, right, addition, and subtraction is like also addition. So you know how to subtract matrices as well. We talk about the division. Sorry, we talk about the multiplication of matrices. Now, what is left in terms of operation is the division, right? Can we divide matrices? The answer is yes, but to do so, we should find inverse of a matrix. Okay, and inverse of a matrix is denoted by A to the -1. Is the matrix where we have A times A inverse is equal to identity matrix. Or if you just switch the order, it's still true, okay? And do all the matrices have inverse? No. There is inverse of a matrix if and only if determinant is not equal to 0. Okay. So what is determinant? Let me show you what determinant is. Normally these concepts are, in linear algebra talked in detail, explained in detail. But in this the class, in differential equations class, I'm just going over them quickly. I hope it's clear. If not clear, as I said you before, try to contact me or just find other sources about these concepts. All right. Okay, how can we find determinant of a matrix? Determinant is just actually assigning a number to each matrix. And to find determinant, it should be always a square matrix. We can talk about determinant of square matrices. And for example, if you have a 2 by 2 matrix A, B, C, D, determinant is A times D minus B times C. By the way, if you see these vertical line segments without bracket sign here and there, it means that it's determinant, okay? And with having that, how can we how can we find inverse of a matrix, right? Inverse is important, quite important. At least for 2 by 2 matrices, inverse can be found with this concept, okay? If we have a matrix A, B, C, D, the inverse is 1 over AD minus BC, and AD minus BC is, as you see here, it is determinant, right? So 1 over the determinant of that matrix times switch A and D and change the sign of B and C, okay? This is how you get the inverse. All right. Okay, these are very quick facts about matrices, but why are we worrying about matrices? Why matrices are really important? Matrices are actually very useful to solve systems of linear equations. And solving system of linear equations is quite important in many different sciences. For example, let's say we have this system. When I say linear equations, I say there is no square root, right? These are all degree 1 terms. So we have 3 unknowns here with 3 equations. Now I can use matrices to solve them, okay? And I can solve matrices to solve this system to find x1, x2, and x3. And how can I do that? First of all, I can represent this system as an augmented matrix. And to get the augmented matrix, you just take the coefficient of x1, x2, and x3, okay? So it is 9, right? 9 coming from that 9, minus 2, minus 6. And let me make a vertical line segment for the equal sign and put 1 here, okay? So negative 8, 3, 6, and 2, 10, negative 2, negative 6, and 3. Now I could represent this linear system, right, with a matrix like that. This is called augmented matrix, by the way. So instead of working on the linear system itself, I can work on the matrix itself, okay, and get the answer. But how can I solve? I'm going to show you an example in the next video. But in general, whenever you have an augmented matrix, you are allowed to swap any 2 rows. You can just switch any 2 rows, multiply a row by a non-zero number, and add a multiple of 1 row to another row, okay? And in general, the deal is actually you are trying to reduce the left-hand side here to the identity matrix. Whatever you have on the right-hand side will be your answers, okay? So let me stop here for this video. In the next video, I'm gonna do some examples, okay? So let me stop share recording. All right, see you in the next video.